Our usual talks are, so does everyone hear me? Do I need to turn something on? Everything? Okay, so, our usual talk are 50 minutes, but research shows that the attention span is about 17 minutes. So I decided to give 3 17-minute talks, and this is the first one. So
we add all our 17 minutes.
What?
We may not be concentrated at the same moment.
Okay, so the first example is of a certain type of random walks with memory that I mentioned in the open problem session yesterday. These are rotor walks, and this is some joint work with Laura Florescu and Lionel Levine. There are fascinating hard questions and cute, easy theorems. So the theorem, everything we can prove is quite easy, so it's published in the Mathematical Monthly. But if you solve the problems, you will publish them in probably a more serious journal. So again, we're talking about rotor walk, which is a deterministic analog of random walk, first proposed by Prijev, Dar, Krishnamurthy under a different name. And this name was given by Jim Propp in 2003. So again, every site in the lattice has an arrow. We will start each arrow in a random direction. And every step, when a particle is at the site, it first rotates the arrow by 90 degrees counterclockwise, and then the particle moves in that direction. So successive exits from a site will cycle through, well, they could start anywhere, and then they cycle through this northeast, southwest sequence. And so in this context, we define an excursion of the particle. So it starts at the origin. An excursion is not one return, but by definition and it starts at the origin, and it has to exit along all 4 edges. So, and then come back. So it's really the 4th return to the origin. So that's one excursion, and this is after 18 excursions what the visited set looks like, and this is after 54 excursions. I think, is Ed here? Yeah, so Ed actually has a nice movie showing this. I'm just showing you still pictures. So one basic question is, at time t, how many distinct sites have been visited? So for perspective, recall that random walks visits up to constant t over log t sites in t steps when we're walking in 2 dimensions. So here is a picture trying to capture different excursion numbers with different colors. So one striking aspect of this model is that each excursion contains all the previous excursions. So it's very different from random walk, where excursions have some independence. Here, each excursion will cover the previous excursion and will also cover the boundary of the previous excursion. So this walk has some nice combinatorial properties. So if AN is the set of sites visited in the nth excursion, and Tn is the total time of all the first n excursions, then in excursion n+1, every site is visited at most 4 times, but the sites in AN in the previous, that were covered by the previous excursion, are all visited, and also each of them is visited 4 times. The boundary of AN is also visited. So just to say, the combinatorial key to this is that if every vertex that has a path pointing to the origin will be visited 4 times, so when we start an excursion, a site has a path to the origin, a directed path, then that site will be visited 4 times. So this you can check by induction along the path. At the end of an excursion, the structure you have is a spanning tree of the vertices visited at the excursion, is a spanning tree directed towards the origin. And hence, everything in that spanning tree is going to be visited in the next excursion. So, and if you want to see more details, it's in the monthly and also on the archive. So in excursion n+1, we said an+1 contains an union the boundary of an. So again, what I'm indicating to you here is a proof of the easy lower bound that says that at time t, we're going to look at times t, which are the ends of excursions. The set covered has a cardinality at least t to the 2/3. So this is a 2/3, but no relation to kpz. The conjecture is that when you have random configuration, this 2/3 is sharp, and simulations show the constant is very close to 6 in that case. But for random initial rotors, we have no proof that it's little o of t. So we're very far from proving a t to the 2/3. The lower bound, which I'm indicating to you now, is very easy, although as far as we know, no one has written it down before our monthly paper, and all the arguments are kind of classical combinatorial arguments. And in particular, one sign that it's easy, it applies to any initial rotor configuration. But some initial rotor configurations will be transient, so some will actually give a range of order t. So this t to the 2/3 lower bound always applies, conjectured to be sharp in the random case, but it's definitely not sharp in the general case. Okay, so this general proof I already started. So an+1 contains an union with the external vertex boundary of an. So this means that the size that an will contain an L1 ball of radius n around the origin, so its size will be bigger than 2n squared. Now, Tn, the total time in the first n excursions, is going to be at most 4n an, because every site in an is visited at most 4 times. Again, let me say why this combinatorial. So in every excursion visits every site at most 4 times, because if you, so look at one excursion, like the first excursion. Suppose some site is visited 5 times. Okay? Let's look at the first site to be visited 5 times. So here's a vertex that's visited 5 times. So it means one of its neighbors must have provided a particle more than once, because, right? So one of the incoming edges must have been used more than once. But if one of my neighbors has provided a particle twice, it means that one must have been visited already 5 times. So so the first one has to be the origin where it all started. Okay, so that's why every site in an excursion, every site is visited at most 4 times, and so the total time is at most the size of an, because an contains all the previous excursions, times 4n, because every site in an is visited at most 4n times in these n excursions. So Tn is at most 4n an, and now 4n is at most root of 8an. You see that from here. Okay, so it means we got Tn is bounded by 2an to the 3/2, so an is at least Tn to the 2/3. Okay, so
this is just combinatorics.
This is just combinatorics.
So is it obvious that an+1 contains an?
Not completely obvious, but yes, it's obvious. So again, the reason is, look at suppose you have a neighbor of the origin with an edge. Suppose we start and some neighbor of the origin has an edge pointing towards the origin. Okay, so so I claim that in an excursion, that vertex has that neighbor has to be visited 4 times. So so once you verify that, you can, by induction, conclude that anything with a path pointing to the origin will be visited 4 times in an excursion. And at the end of the previous excursion, all the nodes in AN have paths leading towards the origin. So the edges here, when a particle leaves a vertex, the rotor is in the direction that the particle left. So at the end of the excursion, we have a structure. The rotors create a spanning tree pointing to the origin. So, okay, there's some thing to think about, but it just follows from the fact that in the previous excursion, all nodes in AN have paths leading to the origin. Okay, so this is the 2/3, and it's, as I said, open to understand any kind of converse under an assumption of random initial rotors. So we can't do that. Let me tell you quickly about some other cases that we can analyze. So one example is the Cobb graph. This is one of my favorite graphs, and it's not only, and I think a few other people. So, so this is just a subgraph of Z2 with the one horizontal line and all the vertical lines, but that's it. So in this Cobb graph, this is how the structure of the visited set looks like. Now, remember, in Z2, we conjectured that the conjecture, actually by Prigiev et al., is that the set of the range of the rotor grows much slower than for random walk, so t to the 2/3 as opposed to t over log t. On the comb, it's provably the other way. So the range of the walk is only growing like root t. So the range is growing very slowly for like root t log t. But this is a classic example where there were previous physics paper. So this is proved with exact calculation by Pach and Tardos. But there was earlier a physics paper claiming t to the 3/4 growth for the range. So, yes.
Vertical, you switch this way and that way. Oh.
So, okay. So first, up here, I'm talking about the range of random walk is root t log t. Now, the range up here, I'm talking about the range of the rotor walk. So the rotor is indeed switching. So at every site, it switches between the 2 possibilities. So.
Is the shape here true parallelogram?
Yes. Yes. So here everything can be analyzed. No curves. No. Okay. And so this is really, because the comb is a tree, you can get through this with one-dimensional analysis. So first, you observe that on the x-axis it behaves like a rotor walk on Z, which will walk up to some point x1, then turn around and walk up to point x minus 1, and so on. And you can determine these locations as sums of geometrics, and you have a similar analysis on each line. So it's easy to analyze random walk in one dimension, rotor walk in one dimension, and you can build on that to analyze it on the comb. And the conclusion is that after you have the rotor walk, the range after t particles is going to be essentially a diamond of size n. So the relation between t and n is is this one, so t is some constant n cubed. And the conclusion is that with this relation between t and n, the diamond that captures RT, so we have diamonds above and below, and they're both of volume 2n squared. So these diamonds are just L1 balls. So because t has order n cubed and the diamond has area 2n squared, then you get this 2/3 relation. So it's the same relation that's conjectured for the plane is proved for the is proved on the comb, but the shape looks different. So one conjecture of Prigge et al. Is that the shape in the plane is a ball. This is not at all clear from the simulations that it's a ball, but the longer the simulations they make, it looks a little more like a ball, but it never is very convincing. Here are two more cases that can be analyzed. So these are some directed lattices. This is the Manhattan lattice where you have one-way streets alternating in direction, right? So, and this is another variant called the F lattice. And again, so here you see this vertex has two edges going out. The one on its left has two horizontal edges going in, and so on. So the odd and even vertices have different directions of the incoming and outgoing edges. Every node has exactly two edges going in and two edges going out, but then they alternate between being vertical and horizontal. So that's on the F lattice. In both of these cases, we can show that rotor walk is recurrent. And I remind you, that's an open problem for Z2. So in Z2, the range appears to be t to the 2/3. It appears to be very recurrent. So there are lots of excursions. But we can't prove it. So we can't prove, in particular, the range is little o of t. On both of these, we can prove recurrence. But the behavior, so the proofs are almost identical for these two cases. The behavior of the actual model seems very different in the two cases. I mean, is very different. This is the range of the rotor walk on the Manhattan lattice after 2 and 11 excursions. So you see this kind of blob growing. This is the behavior on the F lattice. And it seems to, so it is recurrent, but the growth seems to be linear. So the growth could be linear together with recurrence. So, yes.
The lattices are only referring to the initial condition.
No, the lattices, no. The lattices are referring to the underlying graph. The initial, so every node, so thanks for, I should explain this more clearly. So this is the full graph. Instead of working on Z2, we're working on this graph. Okay? And if a vertex has two outgoing edges, then the rotor walk, initial condition will just choose uniformly among these, and then it will just alternate between these two.
Okay. Mm-hmm.
Okay? So look at these two pictures, very different, but in both cases we can prove recurrence by connecting it to the stochastic pinball or a mirror model. So you place at each vertex a mirror with 45 degrees. And so in the classical mirror model, these mirrors are fixed forever. Here, the mirrors are only reflecting the initial condition, and they will turn around. So a mirror tells you when a particle arrives somewhere, where to go next, right? And so the rotors also tell you when a particle will arrive, where to go next. So given a configuration of rotors, you can erect mirrors that will behave like those rotors. But because the rotors are moving, the mirrors are supposed to move in the future too. But it turns out the initial configuration of the mirrors is very important. So in this case, in both of these lattices, if you build the mirrors, you can easily check that on some dual lattice you get a critical percolation. So we know that there will be contours of mirrors that surround the origin, infinitely many contours of mirrors. And then using the combinatorics of the rotor model, what you can check is inside any such cycle of any such contour of mirrors, the particle will complete an excursion before breaking out of the contour. Okay, so that's again a combinatorial lemma. So that ensures at least one return to the origin for each contour surrounding the origin. So you get recurrence, but these contours are so rare that you don't get any good bounds for the range. So we cannot prove in this case that the range is sublinear, and indeed it seems to be sublinear in the Manhattan lattice, but not in the F lattice. But we can prove recurrence in both cases.
And with time, new contours appear, right?
So with time, new contours appear, but then the problem is, are they capturing the particle? So a contour that is created and the particle has already escaped, it's not so relevant. But so certainly the contours that are present in the initial configuration, all of those have to be broken, and for each one we get at least 4 returns to the origin. So, but exactly the difference between how contours are created in the future, that is different in these two lattices. So one challenge is these two lattices are much easier to analyze than Z2, but even then, their understanding the growth of the range is still not done. But not many people have thought about it. Okay, so this tells you the story of the contours, and I'm ending this part by mentioning a few open problems. So again, one problem is in 2 dimensions recurrence, in higher dimensions transience. Again, take 1,000,000 dimensions, proves transience. How hard could it be, right? So we haven't done it. Again, suppose in Z2 you assume recurrence, and now you can use the structure of Z2. Can you use that to prove any upper bound like little o of t? We don't know that one either. There's a lot of other lattices and fractal constructions where maybe one can analyze the range of the rotor walk. And is the shape in 2D actually asymptotic shape actually a ball or not? This we don't know. Okay, so that's the end of the first part. It was a little longer, so I'll have to balance. And the second part is it's very dense. This comes from a question of Benyamini, Kozma, and Shapira, who asked the following. So again, maybe I should. Okay, so you have a random walk in, say, in 3 dimensions, but the random walk uses 2 different measures. Where is the chalk? So we have 2 different measures, mu1 and mu2. Say one of them is like this, and maybe the other one is like that. So you have 2 measures, mu1 and mu2, that describe possible jumps. All we are assuming on these measures is they have bounded range and mean 0. And they are fully 3-dimensional. So unlike this picture, right? So we need some more arrows. So again, we are in Z3, or ZD for D greater or equal 3. And these measures, mu1, mu2, are fully d-dimensional measures, meaning they're not supported on a hyperplane. Okay? So we have these measures, mu1 and mu2. And the question in the BKS paper is, suppose that on a first visit to a site, you use the measure mu1 for your jumps, and on all subsequent visits to a site, you use the measure mu2. Okay? Is this clear again? We're walking in ZD. D is at least 3. And we walk around. If we reach a vertex at the first time, we use the jump distribution mu1. If we are at a later visit, we use the jump distribution mu2. Now, each of these measures by itself, mu1 and mu2, yield a transient walk. Okay? If we are just walking with mu1, it's very classical that this will be transient. The question is, this kind of combination, which is a random walk with memory, could this be recurrent? So, and they also suggested the more general question, where suppose that the mechanism to decide between mu1 and mu2 is a more general adapted mechanism, not just according to the number of visits, but any rule that only depends on the past. Can you find a rule that will make it recurrent? And the answer, the answer, which is in joint work that was published a couple of years ago with Popov and with Perla-Susi, the answer is that with two measures, there is no way to make it recurrent. It's always transient with two measures. Again, when the measures are fully d-dimensional, mean zero, bounded range, it's always transient, no matter what adapted rule you choose to use them. But this is false if you have three measures. So with three measures in 3 dimensions, you can make it recurrent. And the example is mentioned here. So say you're in Z3, you make a step so you look at your 3 coordinates, and if you take in the coordinate which is largest in absolute value, you walk plus minus 1 with high probability, 1 minus 2 epsilon. And in the other 2 coordinates, in each one, you walk with small probability epsilon. Then for small enough epsilon, this walk will be recurrent in 3 dimensions. So that's, again, proved in this paper, which is you can find on the archive or in the Brazilian Journal of Math. And one open question is, what is this? So there is going to be a phase transition in this epsilon. Where is the phase transition? It should be at a quarter. So my conjecture is that for epsilon less than a quarter, this will be recurrent. We do know to show that for epsilon strictly bigger than a quarter, it's transient. So, okay. So, so the key to the proof for 2 measures comes from a calculation with the Lyapunov functions. So take a function which is x to the minus 2 alpha, where alpha is tiny. Okay, and then do a Taylor expansion of this ratio and take expectation. So z is 1 step of the walk. Okay, and when you do this, you get this expression. So let me explain what's going on here. So M is the covariance matrix for the walk. So M, the matrix M is the expectation of Z transpose. So it's the covariance matrix of the walk. And if you look at this, and lambda I are the eigenvalues of this matrix, and trace of M, well, it's the trace of this matrix, which is also the overall variance of the walk. So the sum of the variances of all the coordinates. So when you do the Taylor expansion, you get that the ratio, so we look at the ratio phi before and after the move, take expectation, and what we get, so there's some error which is negligible, and this whole expression turns out to be quadratic, because you have xi squared here and x to the 4th here. And if the trace of M is bigger than twice the largest eigenvalue, then this expression will be strictly negative. Okay, so what it means is, under this assumption, this Lyapunov function will yield a super martingale. right? So it's not, the expectation is going down. And so, and this forces transience, right? Because suppose you start far out, you cannot, so phi is small, you cannot go back to near the origin where phi is large, except with very small probability. So you get transience from the usual Foster criterion, or just super martingale convergence. Okay, so this happens if trace of M is bigger than twice lambda max. And this is just one way to analyze a standard random walk. So if you have a standard random walk, the matrix has a covariance matrix, which is, sorry, the walk has covariance matrix, which is the identity. So in dimension 3 and higher, the trace is indeed bigger than the eigenvalues, which is 1. Okay, so if you want to analyze simple random walk, this is not hard, but it's not, you know, the simplest way. But it's pretty versatile. So now suppose you have, we know that for a standard random walk, even if the covariance matrix doesn't satisfy the condition, it's still going to be transient. If we are using the same measure, then it's still transient. And one way to derive it from this is just to observe that for any covariance matrix M, so for any covariance matrix M, you could always find some other matrix A, so that A, M, A transpose, so this new covariance matrix will satisfy that the trace of M tilde will be indeed bigger than twice the maximum eigenvalue of M tilde. Just by diagonalizing M, you can easily do this. Now, what is this M tilde? M tilde is the covariance matrix of a new process, which is just obtained by applying the matrix A to the original process. So because A is invertible, you know, transience of X tilde is equivalent to transience of X. So this gives you one proof that for any random walk with any covariance matrix, which is not singular, you know, you get transience. But this proof is versatile enough to deal with two measures, because what we proved with Popov and Perla is that for any two positive definite matrices that are 3 by 3, you always can find a matrix A, a single matrix A, so that A, Mi, A tilde will satisfy the condition we want simultaneously for the two matrices. So this is some kind of joint spectral balancing. You have M1, you have M2. You can always find a single matrix A so that AM1 A transpose and AM2 A transpose all satisfy the condition that the trace is bigger than twice the spectral radius. And once you know that, then the Lyapunov function criterion works for this more general adapted walk, because even though you're changing measures, the same Lyapunov function will give a super martingale that goes to 0, and so you get transience. Any questions?
So you can change it a few times, right?
So you can change arbitrarily as long as you change between the two matrices. But with 3 matrices, you can write down 3 matrices, you know, corresponding to the walk I told you before, where there is no choice of such A. One open problem is this condition about existence of A sharp? Okay, so we know more generally than, so I told you about 2 measures, but even if I have 15 measures, if I can find a matrix A that will balance them in this sense, all 15 measures, then I get transience for any adapted walk based on these measures. So the final thing I want to say about, again, stop me if there are any questions, because, yes?
So if you're in 4 dimensions,
yes.
you can do 3 measures and
yes.
balance them?
That's right. So in that paper, we use this argument to say, however many matrices you have, if you can jointly balance them, then you get transience. And so we showed that if we're in d dimensions, you can build d measures that cannot be simultaneously balanced. That by the same idea, you can get d measures that give a recurrent walk. And we conjecture that for any d minus 1 measures, they can be jointly balanced. And that conjecture was proved in a paper which was written last year. And so this is the same Ronen Eldan, the non-ergodic theorist that was mentioned before, and Nazarov and myself. We have a paper that shows that for any d minus 1 measures in ZD, which are fully, the same conditions, mean 0, fully d-dimensional, there is some A that will satisfy this condition simultaneously for all the covariance matrices. Okay, so this is appearing in the Israel Journal of Math. One remaining challenge is, can you find this A constructively? So for the 3×3 case, we give a recipe how to calculate the A. For the higher dimensional case, we give a rather complicated existence proof of the A that uses compactness and variational arguments. So we can't produce the A, but we do prove it exists. Questions? Okay. Third one?
Yeah, question.
Yes.
You said the other direction is open?
The other direction is open, namely, so a particular case which is open, good to focus on, is take in 3 dimensions and take any epsilon less than a quarter, and you walk wherever you are, you walk with probability 1 minus 2 epsilon in the direction of the coordinate, the largest coordinate in absolute value, and with probability epsilon in each of the other coordinates. And the more general question, I can't say really it's a conjecture, but the more general question is this criterion sharp? Namely, if you cannot find such an A, does that imply that there is an adapted walk based on these measures which is recurrent? So this we don't know.
And in that case, adapt means
What?
In that case, adapt means that you've used the first one once, the second one.
No. Adapted means that the choice of which measure to use only depends on your history so far and not on some future thing. So adapted is the minimum requirement. But, okay. Yes?
If you have a stronger rule like that where it's not depending on the trajectory, but
Just on your current location.
yeah.
So I suspect that there's nothing better that you can, the extra power about using the history is imaginary. So using where you are is the strongest thing. But even, right, but so the converse, so a strong form of the conjecture would be if there is no matrix A, maybe then you can always find just a Markov chain where your next choice depends only on your current location, which will give you recurrence, choosing among the given measures. So, don't know that. Okay, so final topic is different, so it's not about random walks with memory, but rather an application of random walks to spanning forests. So first, let me remind you with a picture of Wilson's algorithm, movie of Wilson's algorithm. So this is a way to create a spanning tree in a finite graph. You pick some root, run a loop erased walk and from any starting node until it hits this root. So it might take a while. Then once you do that, start at a different node, run a loop erased walk till it hits the current tree, and keep going. Eventually, you will fill up the whole graph and get a spanning tree, which will be a uniform spanning tree. So this simulation is due to Bostock. Okay. So I want to quickly report in my remaining 17 minutes of a joint work with Tom Hutchcroft on the strange geometry of high-dimensional spanning forests, but I'll really just be able to tell you some of the history and the results. The paper is on the archive. So again, here's a uniform spanning tree. Uniform spanning trees have amazing connections to many things, and this is a partial list. So we had to dig to find a picture of Robin P. Mantle from the time he proved this theorem. So, all right, so uniform spanning forest is obtained by taking a uniform spanning tree in a finite subgraph and taking a limit as the subgraph goes to infinity again. So we have an infinite graph, say, locally finite but arbitrary. Take an exhaustion by a sequence of finite subgraphs. In each one, you pick a uniform spanning tree, and you pass to the limit. If the initial graph is transient, which we will assume, then the spanning forest can be, okay, I'm jumping ahead. So you can do two constructions. So what I told you is called the free spanning forest. There's a construction of the wired spanning forest where outside the finite subgraph, you combine all the nodes to a single node. You pick a uniform spanning tree in this wired graph, and then you pass to the limit. In general, these can give different limits, but in amenable graphs, and in particular in ZD, they give the same limit. We're going to work now in ZD, so this limit is called the uniform spanning forest, wired or free. In this case, it's the same, so just uniform spanning forest. Okay. Now, if a graph is transient, like ZD for D at least 3, then the wired uniform spanning forest can be constructed by a version of Wilson's algorithm rooted at infinity. So what you do is you think of a root at infinity, you run a loop erased random walk. Well, it's going to go to infinity. And then from any starting node, then you start at another node and keep going. And so I'll say more about this in a minute. So this is the wired uniform spanning, the free. P. Mantle showed that in general, in any graph, both limits exist. As I said, in ZD, the two forests coincide, and we call them the USF. So the USF, although it's a limit of trees, it need not be connected. And what P. Mantle showed is it's connected if and only if the dimension is at most 4. So if you're working in ZD, up to 4 it's connected, and higher it's not. And this can be, so when Robin proved this, this was before Wilson's algorithm, so he had to work a little harder. He used the Aldous-Broder algorithm that existed before, but this is much simpler to verify if you know the Wilson algorithm. Okay, so again, this uses loop erased walks that I assume people here know. So you run a random walk, erasing loops as you go. Loop erased walks were first analyzed by Lawler in the 80s. Okay, so for an infinite transient graph, as I said, you can mimic Wilson's algorithm. So you start with the empty forest. Now you create the first forest is the first part of the forest is just built by running one loop erased walk. Now you start at another node and create a loop erased walk, but stop if you hit the existing forest. Okay. Now in some graphs, what will happen is this second loop erased walk might not hit the first one at all. In that case, it's creating a new component, and these components can never be joined later. So once you have two separate components, you're assured to have two components at the end. So this easily yields one direction, namely, if your graph is like Z5, where two random walks started at faraway points are unlikely to intersect, then it follows that the uniform spanning forest will be disconnected. So this way you easily get one direction of Robin's theorem in dimension 5 and higher, where an easy calculation shows random walks don't intersect. And of course, a random walk will also not hit a loop erased walk, so you'll get disconnected forest. The other direction requires knowing a little more. So in dimension at most 4, what you need to know, in order to know that it's connected, you need to know that a random walk will hit a loop erased walk. So luckily, when Robin was considering this problem, this fact was already proved by Lawler a bit earlier in the 80s. So Robin could use this in ZD and conclude that indeed, so this fact in 3 and 4 dimensions was proved by Lawler, and hence Robin could conclude that in dimensions 3 and 4, the uniform spanning forest is connected. He couldn't conclude it as easily as we're doing now because he didn't have Wilson algorithm, but still he could relate the forest to random walk using the earlier algorithm of Aldous Broder and prove this fact. Okay, now this fact is easier because of Wilson algorithm as generalized in this paper to the infinite case. So again, after Pimentel's work, there is a joint paper I wrote with Itai Binyamini, Russ Lyons, and Oded Schramm, where we proved the following generalization. So if you take any graph, any infinite graph, the wire for uniform spanning forest is connected if and only if two independent simple random walks on the graph intersect almost surely. So you don't have to analyze loop erased walks. It's enough to analyze random walks, and if they intersect, then the uniform spanning forest is a tree. So this is based on a inequality that says if two random walks intersect, then also a loop erased walk will intersect a random walk. So this is a general fact valid in any graph. So, okay, so let's go back since clock is running. Let's go back to the structure of the forest. And I want to tell you about one more result with Itai Binyamini, Harry Kesten, and Oded Schramm, which looked at Pimentel's theorem and said, look, in dimension 5, Pimentel tells us there are infinitely many components. But it turns out that any two of these components are adjacent. So there are infinitely many components, but for any two, you can in fact find infinitely many points where they are adjacent. Okay? So it was proved in this paper. And this is true in dimension 5, 6, 7, 8, but it fails in dimension 9. So in dimension 9, if you start at two faraway points and look at their components, with high probability, these components are not adjacent. Okay? So there are lots of trees in the forest that do not touch. And this is true in any dimension higher, but until dimension 12, we have a substitute, namely, for any two trees in dimension 9 to 12, you can find an intermediary. There is some other tree which is adjacent to both. Okay, this is true up to dimension 12, but it breaks down in dimension 13. But in dimension 13, you can find two intermediaries. And you get the picture. So there is a phase transition every 4 dimensions where you need one more intermediary. Another way to put it is to build some abstract graph where a node of this graph is a tree. And, well, 2 trees are adjacent if they come within distance 1 in the lattice. And then what we're saying is that the diameter of this graph is an integer part of d minus 1 over 4. So that's one way to summarize all these facts. Okay, questions? So the statement is very nice and simple. The proofs involve an analysis of loop-erased walks. And in this case, we found an elegant way to prove it using a definition of stochastic codimension or stochastic dimension of a relation in ZD and some inductive argument involving this notion. So this was the situation from 2004. One drawback of this quite nice result is that it doesn't distinguish different dimensions if they differ by only 1. Right? So we expect that dimension 9 and 10 should not be the same, but as far as this theorem goes, they are the same. So this was the question I addressed with Tom, and it turns out to be turned out to be much harder than I expected, but also my co-author was up to the task, and so we can understand the structure and distinguish any dimension. And so any 2 dimensions, the graph, any 2 dimensions above 9 and in some sense above 4, but let's focus from 9 on, the graph I told you changes every dimension. So this graph where the nodes are components of the forest really changes every dimension, although its diameter only changes every 4 dimensions. So here is an example. Suppose you take 3 trees, so 3 components in the forest. For dimension at most 10, we can always find the 4th tree that touches all 3 of them simultaneously. But this is false in dimension 11. So this is a property of the graph which is not captured by diameter, but it allows you to distinguish these dimensions. For 4 trees, we can find the 5th tree that touches all 4 if the dimension is at most 9, but not above. So this distinguishes dimensions 9 and 10. So as I said, the BKPS result can be phrased in terms of the diameter of the component graph of the forest being d minus 1 over 4. And in higher dimensions, the key kind of question is what is phrased here in terms of ubiquitous graphs. So we ask the very general question, given a picture like this, what does this picture mean? So these white circles are pinned components. So we pin, so for instance, in this example, we're asking for, given 4 components, can you find a 5th one which is adjacent to all 4? This asks a more complicated question. Given 2 pinned components, can you find this kind of structure of 4 other components that are adjacent this way, and these 2 are adjacent to this one, these 2 are adjacent to this one. So any kind of finite graph you draw creates a question about subgraphs of the component graph. And by now we can answer for any such diagram, is it ubiquitous? Is it contained everywhere in the uniform spanning forest in a given dimension or not? So I'm going to, so telling you the details of this is going to need a different talk, but I just want to mention that some ideas coming from a much simpler problem, a very classical problem going back to Erdős-Renyi, who asked, given some finite graph, am I going to see it inside GNP? So for that kind of question, you can always calculate the expected number of occurrences of a little graph inside GNP, but that doesn't always tell you the right answer, because there might be a graph where in expectation it occurs often, but there is some subgraph which is an obstruction. And so you have to look not just the expected number of occurrences of a graph, but also for all subgraphs. So some ideas from that Erdős-Renyi theory are needed here, and they have to combine with all this theory of the Wilson algorithm and a lot more. So finally, there is some criterion that allows us to analyze the general case. So I'm going to have to skip this story, but tell you, in the end, there's a condition where you have to, given a graph, you have to, it can be described by connecting balloons to the nodes and weights to the edges and seeing if the graph lifts off. And but I'll have to skip the details of this and just finish with with these examples, since I'm out of time. So I told you that we can distinguish any dimension from 9 on. But what about dimensions 5, 6, 7, 8? So in those dimensions, the graph of components is a complete graph. Any two components touch each other. So if you just look at the graph of components, there is no way to distinguish 5, 6, 7, 8. But Tom insisted on distinguishing those dimensions, and where there's a will, there's a way. So for instance, in 5 dimensions, for every 5 trees in the USF, there is a ball of constant radius that intersects all 5 trees. So this is something that you cannot describe. This is a hypergraph property. It's not a graph property, because 5, 6, 7, 8, you have a complete graph. There's nothing more to say about the graph. But this is a property that works in 5 dimensions, but fails in dimension 6 and higher. In 6 dimensions, every 3 trees, there is a ball of constant radius that intersects all 3. This is not true for more trees, and it fails also in dimension 7 and higher. So this is a way to distinguish dimension 6 and 7. And the final picture, to separate dimension 7 and 8, takes the most sweat. So in dimension 7, given 6 trees, so the white things are given 6 trees in the component, you can always find 3 other trees that correspond to this hypergraph. So what does this picture mean? These 2, together with this one, come within a bounded radius, the same here, and these 3, somewhere else, come within a bounded distance. So this you can always do in dimension 7 and not in dimension 8. Thanks for your attention.
Okay, so there's time for one question.
Yes?
For those, the properties of those forests in the various dimensions, is this just for square lattices, or could you do it for arbitrary?
Same.
Oh.
Thank you. So one thing we prove is, so there is a universality, namely all graphs of polynomial growth are equivalent if they have the same growth. So if you are the Heisenberg group,
If you answer
the 4.
follow-up question, then yeah.
Well.
Okay, so